I want you to, like, picture a scenario for a second. Imagine you're riding a tremendously heavy bicycle, and you're coasting down this massive winding hill.
I am picturing it.
Right. And at the very bottom of this hill, there is a tiny painted parking spot. Your goal is to roll into that spot at the exact right speed so you can just gently apply the brakes and come to a perfectly smooth stop.
Sounds tricky, but solvable.
Yeah, exactly. If you know the weight of the bike and, the slope of the hill, it's basically just a math problem. But now imagine that while you're coasting, the wind keeps suddenly shifting from your back right into your face.
Oh, wow.
And the steepness of the hill randomly changes. And halfway down, a traffic cop just forces you to take a detour completely off your path, yet you still have to hit that exact same tiny parking spot.
Well, at that point, it ceases to be a simple math problem and becomes this constant act of physical and mental negotiation.
Which is exactly what we are getting into today. Welcome to this deep dive. Today, we have a really unique stack of sources for you. We are looking at official, highly technical Airbus A320 flight crew training manual excerpts.
Right.
Specifically, we're diving into the sections that cover approach strategies, energy management, and waypoint sequencing.
And I mean, these documents are essentially the blueprints. It's what commercial pilots use to learn how to communicate with and really manage the aircraft's internal computers.
Yeah, and our mission today is to translate these incredibly dense aviation manuals, and they are dense, into a clear picture of how pilots actually collaborate with their flight computers, and sometimes, have to outsmart them entirely.
Absolutely.
Just to safely get a massive passenger jet from cruising altitude down to the runway. Because the overarching theme in these manuals isn't just about steering a plane, it's about a whole philosophy called energy management.
Right. And energy management is the core of modern aviation. When a modern aircraft reaches what's called the top of descent, which is the geographic point where it begins its journey down to the destination airport.
Right, the top of our imaginary hill.
Exactly. At that point, the flight management system, or the FMS, has already computed this flawless three-dimensional mathematical path down to the runway.
So it's got the perfect slope figured out.
Yes. And it does this to maximize efficiency. The computer establishes what they call an idle segment. The whole idea is to pull the engine thrust all the way back to flight idle and essentially glide down this computed path to conserve as much fuel as possible.
Makes sense.
But the FMS calculates this math based on a snapshot of wind data that was entered, hours ago.
Yeah.
And the actual atmosphere is this fluid, constantly changing environment.
Which is a huge deal, right? Because if you are essentially gliding a 60-ton piece of metal, the wind suddenly becomes the defining factor in your kinetic energy.
Oh, absolutely. The manuals illustrate this beautifully. If the aircraft encounters a stronger headwind than the computer anticipated, it faces more resistance.
Like biking into the wind.
Right. So it loses energy relative to the ground, and the plane will physically drop below that computed mathematical path. And on the flip side, if you get a sudden tailwind, it pushes the aircraft, it adds excess kinetic energy, and causes the plane to float above the optimal path.
Wow, okay. But the most counterintuitive part of this entire manual, at least to me, has nothing to do with the wind. It's actually the plane's own internal systems messing with the physics of the glide.
You're talking about the engine anti-ice system.
Yes. So let's unpack the mechanics of this for you listening, because the manual warns that turning on the heaters to melt ice on the engine cowlings actually makes the plane speed up, and it pops above its safe glide path.
It does.
But why? Why would a heating system affect the forward speed of a gliding airplane?
Well, it comes down to how a jet engine actually generates that heat. The system doesn't use electric coils, like a toaster.
Yeah.
It uses bleed air. The engine takes incredibly hot, highly compressed air directly from inside its own turbine core, and it routes it through pipes to the leading edges of the engine cowlings to melt the ice.
Wait, so you are basically tapping into the engine's internal pressure to act as a heater.
Exactly. And because you're bleeding off that vital internal pressure, the engine's control computer has to step in to protect the engine from accidentally flaming out and shutting down.
Oh, I see.
So to maintain stability, it automatically commands the engine to spin faster.
Yeah.
It actively increases the idle RPM.
Hold on. So even though the pilot's throttle levers are physically pulled all the way back to the idle position, the engine is just revving higher than the flight computer planned for?
Precisely. It introduces unexpected forward thrust into an equation that entirely relies on gliding. So the aircraft is suddenly producing more thrust than the FMS accounted for,
Right.
and it gains excess potential energy, and it starts to balloon above the vertical profile.
Okay, so if I'm picturing this correctly, since the plane is largely flying itself at this point, my assumption is that the autopilot detects that extra speed and just, I don't know, pulls the throttles back to fix it?
Well, it can't,
Yeah.
because the throttles are already at their physical minimum. They're at flight idle.
Oh, right.
There is no more back to pull them. So the autopilot defaults to its secondary method for bleeding off speed.
Which
It
is...
pitches the nose of the aircraft up.
Wait, it pitches up, but that takes it completely off the descent path. It's trying to maintain the speed limit, but in doing so, it just destroys the downward trajectory.
Yeah, this is a classic automation trap.
Yeah.
The autopilot is doing exactly what it was programmed to do, right? But without human intervention, it will fly the aircraft dangerously high above the required path.
That is wild. But the Airbus does give the pilots a specific tool to monitor this, right? Like the cockpit has a vertical deviation indicator on the main screen.
Yes, pilots affectionately call it the VDEV, or the Yoyo.
The Yo-Yo. I love that.
It's a small green circle on the display. When the plane is too high, this yo-yo drops below the center line, visually indicating that the correct path is now physically below the aircraft.
Okay. And the manual details a really fascinating feature on the navigation display to help fix this. Because it doesn't just, leave the pilots guessing how to get back down.
Right.
It generates something called a predicted path, assuming half-speed brakes.
Yeah, that's a brilliant feature. The computer basically draws a steeper, converging blue line on the map screen. It shows the pilots exactly where the aircraft's current trajectory will successfully intersect with the optimal descent path.
Assuming they deploy half of their speed brakes.
Exactly.
And speed brakes being those large panels on the top of the wings that flip up to disrupt the airflow, kill the lift, and basically create massive drag to force the plane down.
Right. They are a pure energy management tool. And the training manual actually offers a fantastic tactile tip for instructors to pass on to new pilots regarding this exact scenario.
Oh yeah, this was cool.
It dictates that whenever a pilot reaches up to the overhead panel to push the engine anti-ice button, their other hand should instinctively move down to rest on the speed brake lever.
That is so smart. So you don't even wait for the computer to realize you were too high.
Nope.
You anticipate the aerodynamic change before the yo-yo even moves,
Yep.
and you manually deploy the drag to capture that intercept point yourself.
It perfectly illustrates human anticipation overriding computer reaction.
Okay, so you've recognized the ice, you've managed your speed brakes, and you've successfully tricked the autopilot into getting back on the computer's digital path.
Right.
But you're still sharing the sky with hundreds of other planes, which means you rarely get to stay on that perfect digital path for very long.
This brings us to the human element outside the cockpit. Air traffic control.
Right. The manual calls this the radar vector trap. So all of your energy management so far relies entirely on that VDEV yo-yo telling you the absolute truth about your vertical position. But then air traffic control comes over the radio and gives you radar vectors. What does that actually mean?
Well, a radar vector is simply ATC giving you a specific compass heading to fly. So they might say, turn right to 090.
Right.
They do this to space you out from other traffic or maneuver you around a storm. But the catch is, when you turn onto that new heading, you are physically leaving the meticulously planned lateral path that the FMS programmed.
Okay, this feels a lot like when your car GPS tells you to turn left, but you see a massive traffic jam and decide to just take a detour down a side street.
Yes.
The GPS map still shows your intended route, but you are actively driving away from it.
The underlying logic is remarkably similar. But obviously, the stakes are a bit higher in a jet. The flight plan in the computer consists of sequential waypoints in the sky. If you were programmed to fly over waypoint A and then waypoint B, but ATC vectors you 3 miles to the right of them.
The flight computer doesn't intuitively know you're skipping them.
Exactly. It assumes you still need to go to waypoint A.
So it just gets stuck in the past.
Yeah, it stubbornly retains waypoint A as the active TOWPT, the tow waypoint. And if that active waypoint is now geographically behind the aircraft, the FMS cannot compute a valid forward trajectory down to the runway. The geometry literally breaks.
Which means the yo-yo breaks.
The vertical guidance completely freezes. The VDEV indicator just becomes a meaningless green circle precisely when energy management is most critical.
Oh, man. And to fix this, you can't exactly just pull over and reboot the airplane. The pilots have to manually step in and manage the computer using the MCDU.
Right. The MCDU, or Multipurpose Control and Display Unit, it's the physical keyboard and screen located on the center pedestal between the two pilots. It's essentially the primary interface for typing commands into the flight computer.
And the manual is incredibly specific about the choreography here. Like, it dictates very strict task sharing.
It does.
The pilot flying, who is the one whose hands are on the controls managing the current trajectory, calls out the command. And the pilot monitoring, the one handling radios and systems, actually physically types on the MCDU to clear the bypassed waypoints using the CLR key.
But the manuals emphasize a golden rule that absolutely must not be broken during this process. You must manually clear those old waypoints only when the aircraft is physically beyond them.
Okay, wait, why the delay? If ATC gives you a detour that clearly bypasses waypoint A, why not just hit delete on waypoint A the second you turn the plane?
Because of how the computer calculates geometry.
Okay.
The FMS is constantly drawing a curved path from your current position to the next active waypoint.
Right.
If you clear waypoint A while you are still, say, miles away from the turn, the computer instantly draws a new line from your current position straight to waypoint C.
Right.
But that isn't the path you're actually going to fly because ATC hasn't told you to turn back yet.
Oh, I see. So if you delete it too early, you distort the calculated distance.
Which completely ruins the vertical descent math.
Wow. So you literally have to wait until the aircraft is laterally past the point, then clear it. So the computer logically locks onto the correct upcoming waypoint ahead of you.
Exactly. And once that happens, the computer establishes a valid forward path, and the VDEV Yoyo snaps back to reality. It starts giving you honest vertical guidance again.
That's incredible. And the training manuals offer this really great mental anchor for the pilots on this. They say to constantly interrogate the navigation display.
Right.
Like, if your active to waypoint is physically drawn ahead of your little airplane icon on the screen, then the VDEV Yoyo is telling the truth.
Yes.
But if the waypoint is drawn behind your airplane icon, you must completely disregard the VDEV.
It's a prime example of why pilots cannot afford to blindly follow the magenta line on a screen.
Yeah.
They have to constantly verify that the automation's internal logic actually matches the physical reality of the airspace.
Okay, so you've battled the thermodynamics of the ice, you've deployed the speed brakes, you've manually cleared the stubborn waypoints after ATC took you off course.
Yep.
The computer is finally honest again. And this all culminates at what the manuals refer to as the final descent point, or FDP.
The FDP is a critical threshold in the sky. It marks the transition from the descent phase into the actual approach to the runway.
And the manual outlines that the crew uses the MCDU to verify some very specific parameters at this point. There's the flight path angle, the specified altitude, and the missed approach point.
And these aren't just arbitrary terms. They are the physical architecture of the approach.
Okay.
The specified altitude is the exact height you must be at to safely begin your final drop. The flight path angle is the physical downward slope toward the runway, which is usually about 3 degrees.
Right.
And the missed approach point is a literal invisible line in the sky. If the pilots reach that exact coordinate and cannot visually see the runway environment, they are legally required to apply full power and climb back up.
A go-around.
Exactly.
So the biggest decision the crew has to make before they hit that final descent point is how they're going to physically configure the airplane for the actual landing. And the manual outlines 2 strict strategies for this.
Right. You have the early stabilized approach and the decelerated approach.
Early stabilized sounds fairly self-explanatory, but let's just look at the mechanics of it. The plane arrives at the final descent point fully configured for landing. The heavy landing gear is down, all the wing flaps are fully extended, and the plane has already slowed down to its final approach speed.
Right. And aerodynamically, that creates a massive amount of drag.
Yeah.
Pushing a fully configured aircraft through the sky requires a significant amount of engine power just to maintain speed.
Okay. But the decelerated approach operates on a completely different philosophy, right?
Mhm.
The aircraft arrives at the final descent point in what the manual calls Configuration 1.
Yes, meaning only the slats, which are the small panels on the front leading edge of the wing, are deployed. The main flaps and the landing gear are still tucked away, so the aircraft is flying at a faster speed, known as S-speed.
So the rest of the process, bleeding off that speed, extending the landing gear, dropping the main flaps in stages, all of that happens dynamically while the plane is actively descending down that 3-degree slope.
Exactly. And when we compare the two, an early stabilized approach gets the heavy workload done miles away from the runway. It is highly predictable and very safe.
Blah.
The trade-off is efficiency. Flying with all that drag extended for a longer period burns considerably more fuel and generates a lot of noise over residential areas.
It's like putting your car in first gear a full mile before you reach a stop sign.
Right.
You have total control, but the engine is screaming and you are burning a ton of gas.
Exactly. Whereas the decelerated approach manages the energy dynamically, bleeding off speed exactly when you need to.
Yeah.
It is much more fuel efficient and quieter, but it demands very active, precise management of the aircraft's energy state during a highly critical phase of flight.
But regardless of which strategy a crew briefs, the manual imposes these absolute unbreakable rules about when the plane must be quote-unquote stabilized.
Yes. The aviation industry refers to these as gates. A gate is a hard altitude limit. When passing through a gate, the aircraft must be fully stabilized, meaning the gear is down, flaps are set, it is on the correct speed, on the correct path, and the engines are spooled up and providing stable thrust.
And the sources state that if you are flying in instrument meteorological conditions, meaning, bad weather, heavy rain, or flying through clouds, you must pass through this gate at exactly 1,000 feet above the airfield level.
Right. And if it is a clear sunny day, visual meteorological conditions, the gate is lowered to 500 feet above the airfield.
Okay.
But if you cross those altitudes and the plane is not perfectly stabilized, the manuals dictate only one acceptable action, a go-around. You abort the landings, throttle up, and try again.
The manuals actually explicitly warn that arriving underconfigured on an early stabilized approach is a major crew error. It demands flawless coordination. But even as the plane gets this close to the ground, the manual is still throwing up complex warnings about automation. There's this fascinating note about something called alpha prot.
Yes. The relationship with the autopilot remains highly conditional right down to the runway. Alpha prot is a stall protection feature. It monitors the aircraft's angle of attack, which is the angle of the wing relative to the oncoming air.
Right. And if you point the nose too high, the air stops flowing smoothly over the top of the wing. It separates, becomes turbulent, and the wing just stops generating lift. That is a stall.
Exactly. And if the computer senses the angle of attack reaching a critical limit alpha prot it prioritizes keeping the plane flying over whatever the autopilot is trying to do.
Wow.
The system will automatically disengage the autopilot and physically force the nose of the aircraft down to regain smooth airflow and prevent a stall.
That's crazy. And the final warning in the manual involves the instrument landing system screens at the very end of the approach, like just feet above the ground.
Yes, the instrument landing system, or ILS, relies on physical radio antennas on the ground projecting a cone of guidance into the sky. You have a localizer beam for left and right guidance and a glide slope beam for up and down guidance.
So the computer reads these radio beams and displays them as crosshairs on the pilot screen.
Right. But as you get incredibly close to the runway, to a point called the minimums, the aircraft actually physically flies over or past these antennas.
Oh.
And because of that, the radio cone narrows so drastically that the geometry breaks down. The glide slope deviation indicator on the screen becomes hypersensitive and will start giving wild, false readings.
So the manual explicitly instructs the pilots to physically turn the LS push button O-off-F at minimums.
Yes.
They literally have to turn off the radio display so they don't get distracted by a lying screen right at the most critical moment of flaring the aircraft for touchdown.
It is a constant, highly choreographed dance between leveraging machine efficiency and maintaining human situational awareness.
Which really brings us back to you listening to this. The next time you are sitting in the window seat of a passenger jet and you start your descent, pay attention to the environment around you. Like if you hear the engine spool up strangely while you feel like you should be gliding.
Or if you feel the sudden, heavy rumble of the speed brakes popping up on the wing.
Exactly. You will know exactly what the flight crew is battling up front.
Because they aren't just pointing the nose down and steering a steering wheel.
No. They are mathematically managing excess energy. They are fighting the thermodynamics of anti-ice bleed air. They are actively interrogating the flight computer to keep it from living in the past after air traffic control changed their route. And they are managing drag to hit invisible, strict gates in the sky at exactly 1,000 feet.
And, the source material leaves us with a rather profound takeaway, I think.
Yeah.
These incredibly advanced Airbus manuals repeatedly warn the pilots of two things. First, the autopilot will actively pitch the plane into danger if it doesn't understand the physics of anti-ice drag. And second, the navigation screens will absolutely lie to you if you don't manually clear old bypassed waypoints. The computer only knows what it knows.
Right. It has no context outside of its programming.
And as we integrate more and more artificial intelligence and automation into our own daily lives, from the cars we drive to the algorithms that help us make business decisions, this raises a pretty crucial question.
It is.
At what point does the underlying assumption that the computer knows best become our biggest liability? Are we, in our own lives, remembering to manually clear our own bypassed waypoints, or are we letting the machine dictate our trajectory based on outdated data?
That is a phenomenal thought to end on, because just like at 30,000 feet, if the machine is stuck in the past, it just cannot safely guide you to where you need to go. Thank you for joining us on this deep dive into the invisible physics and high-stakes automation of flying. Keep questioning the world around you, keep looking for the why behind the what, and we will catch you on the next deep dive.